Good evening, everybody. We have, as Bodhi just indicated, two fairly diverse topics today, design for torsion and also the basic non-seismic detailing of concrete structures. The original plan was for Dr. Yazdani to speak on pre-stressed concrete today. I told you so at the end of the lecture yesterday. This lecture was going to be tomorrow, but Dr. Yazdani informed us late in the afternoon, our time yesterday, that he was not going to be ready to deliver his lecture today. So at that point, I had to scramble to prepare to do this class today. Hopefully, it will go all right. But I wanted you to be aware that of this change of plan. Dr. Yazdani now is scheduled to speak tomorrow on pre-stressed concrete. So I'll do the torsion design first and then non-seismic detailing. The two topics are difficult to fit into the time we have. So I will not try to do a torsion design example. Torsion design, a designer commonly does not have to do. In any case, if you need to do it, there are examples available in several sources. We just don't have time to fit that in. The non-seismic detailing, I think, is vitally important, and I don't want to take time away from that. Now, the torsion design procedure that we have in ACI 318, I believe this came into the code in the, let me see, 18, anyway, 31802 or earlier. The current procedure, which has been in there since then, is based on thin-walled tube space truss analogy. The procedure applies to non-pre-stressed and pre-stressed concrete members alike. It applies to solid and hollow sections, and the method adopted by ACI assumes that torsion is resisted by transverse reinforcement and by longitudinal reinforcement, additional longitudinal reinforcement that we add for torsion. This is in addition to what we have for flexion. The combination of the transverse reinforcement and the additional longitudinal reinforcement resists the tension with no help from concrete. That is the idea. So that's the thin wall tube analogy of ACI 318. So the design for torsion is based on a thin wall tube space truss analogy. Once a reinforced concrete beam has cracked in torsion, its torsional resistance is provided primarily by closed stirrups and longitudinal bars located near the surface of the member. So the closed stirrups, the word closed here is very important, and we will discuss it later. So torsional resistance is provided primarily by, it's not primarily, it is entirely by closed stirrups and longitudinal bars located near the surface of the member. In the thin wall tube analogy, the resistance is assumed to be provided by the outer skin of the section, roughly centered on the closed stirrups. So the outer skin roughly centered on the closed stirrups. Both hollow and solid sections are idealized as thin-walled tubes, both before and after cracking. So a solid section will also be treated as a thin wall tube for the purpose of torsion design. The cracking torsion under pure torsion, meaning no bending moment, no shear to go with it. The cracking torsion under pure torsion is derived by replacing the actual section with a thin wall tube with a wall thickness T prior to cracking and an area enclosed by the wall center line that is equal to A sub 0. Okay. So we are assuming we will calculate our cracking torsion by replacing the actual member section that we have with a thin wall tube that has a wall thickness T, and we will see what this T is, and an area enclosed by the wall center line equal to A sub 0. This wall center line will become clearer as we go. Okay. Some important notation: A sub CP, area enclosed by outside perimeter of concrete cross section. This is pretty strange language. It is not cross-sectional area, but area enclosed by outside perimeter of concrete cross section. The idea is if it is a hollow section, we will count the area of the hole. Okay, so there will be, you see what I'm saying? If it is a hollow section, then there is a big difference between the cross-sectional area and the area enclosed by outside perimeter of the concrete section. The area enclosed by the perimeter includes the area of the hole, and that's what is meant. Okay, so area enclosed by outside perimeter of concrete cross section, A sub 0, is gross area enclosed by shear flow path, and we will look at that. We called it area enclosed by wall center line also. P sub CP is outside perimeter of the concrete cross section. So A sub CP, P sub CP, P sub CP is the outside perimeter, A sub CP is the area enclosed by that perimeter. Okay, this is the thin wall tube that we have been talking about. The thickness is T. Let me maybe go to this page and then get back to the other page. Okay. So in a closed thin walled tube, exactly what we were looking at, the product of the shear stress and the wall thickness T at any point in the perimeter is known as the shear flow Q. Q is equal to the shear stress tau multiplied by the wall thickness T. The shear flow Q due to torsion acts as shown in figure 11.5a. That's the figure out of the ACI 318 commentary. And this is the figure. So shear flow, if this is the direction of torsion, then shear flow is as shown in the picture by the arrows. Okay, so sorry. No, it doesn't go back somehow. The shear flow Q due to torsion acts as shown in the figure that I just showed you and is constant at all points around the perimeter of the tube. The path along which it acts extends around the tube at mid-thickness of the walls of the tube. At any point along the perimeter of the tube, the shear stress due to torsion is tau equal to T, the torsion causing the stress, divided by 2 A sub 0 times T, where A sub 0 is the gross area enclosed by the shear flow path. Okay, so this is a basic relationship from strength of materials. A sub 0 is the gross area enclosed by the shear flow path, and that is shown in the second part of the picture. So this is the shear flow path, and the area enclosed by that is A sub 0. This is also area enclosed by the wall central line, the central line of the thin wall tube. Okay. A sub 0, very important notation. So at any point along the perimeter of the tube, the shear stress due to torsion is T, the torsion causing the stress, divided by 2 A sub 0 T, where A sub 0 is the gross area enclosed by the shear flow path. And T is the thickness of the wall at the point where tau is being computed. The shear flow follows the mid thickness of the walls of the tube, and A sub 0 is the area enclosed by the path of the shear flow, as has been said before. Okay. So this is a summary pretty much of what I read. This is the torsion that is twisting the member, causing shear stress in the walls of the thin-walled tube. The P sub Cp and A sub Cp I have explained to you. The Q shear flow is T over 2A0 as was written on the next page. This is from strength of materials basically, okay, and the thickness of the tube is 3/4 of the area enclosed A sub Cp divided by P sub Cp, and A sub 0 is 2/3 of A sub Cp. Okay, those are the relationships defining the thin wall tube of ACI 380. Now, this is extremely important to understand what is on this page. Okay, so we design for a required torsional strength. This is the design torsion acting on our member. There is a threshold torsion defined in ACI 318. Threshold torsion is 1/4 of the cracking torque, the torsion that causes torsional cracking of the member. We can figure that. Okay. So if the applied torsion, the required torsional strength T sub U, is less than the threshold torsion, 1/4 of the cracking torque, then we can simply ignore that torsion. There is no torsional design in that case. The torsion is too small to count. If, however, the required torsional strength is larger than or equal to the threshold, 1/4 of the cracking torque, now we will have to design for torsion. Now we will have to figure out if the torsion is equilibrium torsion or compatibility torsion. And we will define that later. I have a couple of pictures. Equilibrium torsion is something that is, how should I say, we have no choice but to design for T sub U, the torsion acting on the member. We cannot redistribute part of it away. So that torsion is needed for the equilibrium of the member. Compatibility torsion, on the other hand, by definition means that if we decide to design for something lower than T sub u, that would be permitted. The difference between T sub u and whatever torsion we decide to design for will be redistributed, will become larger bending moment into the slab or whatever is causing the torsion on the member. You will see this more graphically just a little bit later. Okay. Now, when we decide not to design for the entire T sub u, we cannot go below the cracking torque. We have to design at least for the cracking torque, T sub CR. And the remainder, the difference between the required torsional strength and the T sub CR, the cracking torque, can be distributed away. Okay. So when T sub u is larger than or equal to threshold torsion, we have to design for torsion. If it is equilibrium torsion, then we have to design for the entire T sub u. We have no choice. If it is compatibility torsion, we may design for T sub CR or something larger, and then whatever we did not design for, the part of the torsion, required torsional strength that we did not design for, will be redistributed away to other structural members. Okay, this is how ACI 318 is set up. And this threshold torsion, you have to, this whole concept you have to understand. It shall be permitted to neglect torsion if the factor torsional moment T sub u is less than, for non-pre-stressed members, this is the expression for the threshold torque. In US units, it's 1 square root of F sub C prime A sub Cp squared divided by P sub Cp. P sub Cp, remember, is the perimeter of the thin wall tube, and then A sub Cp is the area enclosed by that perimeter. Okay, so one P sub Cp outside perimeter of concrete cross section, A sub Cp area enclosed by outside perimeter of concrete cross section. Very important notation that we have to keep in mind, because that will be carried throughout. So threshold torsion for non-pre-stressed members is given by this expression, and this is 1/4 of the cracking torque. Cracking torque happens to be 4 square root of F sub C prime A sub Cp squared by P sub Cp. 1/4 of that is the threshold torsion. Torques that do not exceed approximately 1/4 of the cracking torque will not cause a structurally significant reduction in either the flexural or shear strength and can be ignored. So any torsion less than the threshold value can be ignored. We don't have to design for it. If the member in question is subject to an axial tension or compression, then the expression for threshold torque is modified by that. Okay, so for regular non-pre-stressed members without any tension or compression, this was the expression. If you have a tension or compression applied, this is the expression for threshold torsion. N sub u is the factor axial force normal to cross section occurring simultaneously with V sub u and T sub u, and N sub u is positive when it is compression, negative when it is tension in that expression. For members, so threshold torsion, when we have overhanging flanges, as in this picture, the A sub CP, P sub CP, the section resisting torsion is as shown in the picture. This is as in two-way slab design. We include a portion of the slab in the torsional member. Maybe we should read for members cast monolithically with a slab, the overhanging flange width used in computing A sub CP and P sub CP shall conform to whatever we did in the two-way slab chapter. There are other things here. So the overhanging flange that will be included in the section is whatever is sticking below the slab, this distance H sub B, but it will be no larger than 4 times the thickness of the slab. When there is an overhang on both sides, we get B sub W plus 2 times the overhang, and then the overhang cannot be any larger than 4 times the flange thickness as mentioned earlier. Okay. Now, the other thing that was said here, for a hollow section, A sub G, the gross cross-sectional area, shall be used in place of A sub CP in section such and such, and the outer boundaries of the section shall conform to those details. I'll let you look into. You have to go to the section numbers. This is coming back to that. So for hollow sections of non-pre-stressed members and non-pre-stressed members subject to tensile or compressive force, replace A sub CP with gross cross-sectional area. Okay. Remember, the difference is A sub CP includes the whole, A sub G does not include the whole. So replace A sub CP with A sub G. The reason for replacing A sub CP with A sub G, I will give you the first reason. The second one is too complicated. You have to read the ACI commentary to understand it. Why we replace A sub CP with A sub G for a hollow section? Cracking torque of a hollow section is approximately A sub G over A sub CP times the cracking torque of a solid section with the same outside dimensions. Okay, so this is why it is important to do what is suggested here. For hollow sections, replace A sub CP with A sub G. For torsion, this is commentary. All R sections are commentary to 318. For torsion, a hollow member is defined as having one or more longitudinal voids, such as a single cell or multiple cell box girder. That would typically be a hollow section. And then the commentary is suggesting ignore voids for any ungrouted post-tensioning ducts because they are small. Typically, A sub G over A sub CP ratio will be larger than or equal to 95%. So those little voids don't count. Okay, when we say for a hollow section, replace A sub CP with A sub G, we don't mean a section with a few ungrouted post-tensioning ducts. Okay, so we are back to threshold torsion. For isolated members with flanges and for members cast monolithically with a slab, the overhanging flange width used to compute A sub CP and P sub CP shall, I showed you pictures, this comes from the slab chapter, except that, this is what is new on this page, except that the overhanging flanges shall be neglected in cases where the parameter A sub CP squared by P sub CP calculated for a beam with flanges is less than that computed for the same beam ignoring the flanges. So So this ratio, A sub Cp squared P sub Cp, when you include the flange with this beam section, and A sub Cp squared over P sub Cp goes down, there must be cases where it happens. I can visualize one right off the bat. But in any case, if that happens, then you ignore the overhanging flange. Then this is the section of your torsional member. So you will not decrease the A sub Cp squared by P sub Cp ratio by including the flange in the torsional member. Okay, if the factor torsional moment T sub u, this is the required strength, this is the applied torsion, is required to maintain equilibrium if the factor torsional moment T sub u in a member is required to maintain equilibrium and exceeds the minimum value, the threshold torque, the member shall be designed to carry T sub u in accordance with section such and such. Okay, so the threshold torque in a statically indeterminate structure where reduction of the torsional moment can occur due to so this is equilibrium torsion. The member shall be designed to carry T sub u, and let me come back here. Let me show you. Okay, so this is a good illustration out of the commentary to ACI 318 of equilibrium torsion. Okay, so this is a frame, let us say, with a cantilevered slab. Any loading on that slab will cause torsion on this beam. Okay, and that that torsion keeps the loading on the slab in equilibrium. There is nothing else. So if we don't design that beam for that torsion, then there will be collapse of the slab. There will be failure of the beam leading to the collapse of the slab. Okay. So this is equilibrium torsion, as opposed to this situation where, you know, those the slabs and the beams cause torsion on this spandrel beam. It's very easy to visualize that. Okay, this slab system is loaded with out of plane load, vertical load. That loading causes torsion on this beam. However, if we do not design this beam for all the torsion that the beam is subject to, whatever torsion we do not design for will become additional bending moment in those beams and slabs. Okay, it will become additional bending moment in the slab system. There will be redistribution of the torsion that we decide not to design for. This is compatibility torsion, much more common than equilibrium torsion. Okay, so let's get back now. If the factor torsional moment in a member is required to maintain equilibrium and exceeds the threshold value, the member shall be designed to carry T sub u. In a statically indeterminate structure, where reduction of the torsional moment in a member can occur due to redistribution of internal forces upon cracking, the maximum T sub u shall be permitted to be reduced to the values given as follows. And this is the expression for cracking torque, 4 square root of F sub C prime A sub Cp squared over P sub Cp. So we can reduce the T sub u to T sub Cr decide to do our design for T sub CR. We cannot go any lower than that. We have to design at least for T sub CR, because until there is cracking, there is no redistribution. Unless the beam cracks in torsion, it cannot redistribute torsion. So we cannot go below the cracking torque. If it is a non-pre-stressed member with axial tension or compression applied, then this is the expression for cracking torque, as we have seen before. The correspondingly redistributed bending moments and shears in the adjoining members shall be used in the design of those members. Again, for hollow sections, A sub CP, not again, in this situation, in these computations, for hollow sections, A sub CP shall not be replaced with A sub G. Okay, so we said that you shall replace A sub CP with A sub G in the calculation of the threshold torsion and so forth. Okay, reason for replacing, we said replace okay, in calculating the threshold torque, we have A sub CP squared over P sub CP. A sub CP and P sub CP shall include the flanges, and that's where we said replace A sub CP with A sub G for hollow sections. But then when we are designing for torsion, we have compatibility torsion. T sub U is the applied torque. We have chosen to design for T sub CR. The remaining torsion becomes additional bending moment in the structural members that are causing the torsion on the spandrel. In that situation, we shall not replace A sub CP with A sub G. Okay, this I have shown you: equilibrium torsion, compatibility torsion. Compatibility torsion, this is further description when the torsional moment exceeds the cracking torque. A maximum factor torsional moment equal to the cracking torque may be assumed to occur at the critical section near the faces of the supports. This limit has been established to control the width of torsional cracks. The T sub CR, if you design for that, then the width of the torsional crack will be limited to what we consider to be acceptable. This simply shows that when a beam cracks in torsion, the stiffness goes down drastically. Okay, so initially as there was twisting of the member, it was carrying more and more torsion, but then it cracks in torsion at a certain torque. The torsion drops drastically, and then it takes a lot more twist to get back to cracking torque, and then with further twist, the member can resist more torsion. And if we decide to design for that, then the extra torsion, the difference between this and that, will have to be redistributed. That will become additional bending moment in the slab system that is contributing torsion. Unless determined by a more exact analysis, it shall be permitted to take the torsional loading from a slab as uniformly distributed along the member. So this is the slab, the loading on which is causing torsion on the beam, on the spandrel beam, as we call it, peripheral beam. That torsion, if the loading on the slab is uniform, then that torsion is also considered to be uniformly distributed along the span of the spandrel. That's all that we are saying. There is no basis to assume anything else. In non-priestess members, sections located, this is like the critical section for shear. So in non-priestess members, sections located less than a distance d from the face of a support shall be designed for not less than T sub u, computed at a distance d, etc. So all of that tells you that the critical section for torsion is a distance d away from the support face, unless there is a concentrated torque applied within that d distance, in which case we we back the critical section off to the support face. If it is a pre-stressed member, then the critical section is 1/2 of the total depth away from the support face, not the effective depth. D is replaced by h/2. This is a beam being tested under torsion, and what you should be able to clearly see is that torsion causes spiral cracking. Okay, you know, we are all familiar with spiral, and spiral cracking is characteristic of torsion. When you see spiral cracking, you know that torsion is causing it. And in those diagonals, there is compression. The diagonals, concrete diagonals between the cracks, are in compression. Those are compression members. Now, if you keep on increasing the torque, initially the corners of the cover will begin to spall. You know, the concrete is under compression. If the compression becomes high enough, the concrete will begin to spall, typically at the corners, and then it will spread, and ultimately we will lose much of the cover. So in torsional design, we depend basically only on the steel cage. Also, very importantly, because the cover will be lost, we have to make sure that the reinforcement, both the transverse reinforcement and the longitudinal reinforcement, is anchored in the core concrete, the concrete inside the cage. Okay, we cannot depend on the cover concrete to anchor the longitudinal or the transverse reinforcement. Okay. Now, this is like when we say the shear on a member shall not exceed h square root of f sub c prime or whatever, because beyond that there is compression cracking. So it is that kind of a limit when a member is subject to combined shear and torsion. And that is pretty much always the case. Pure torsion is very rare. It is almost always shear and torsion acting on a structural member. Okay. So the cross-sectional dimensions shall be such that for solid sections, the shear stress squared divided by the torsional stress squared. This term is T sub u P sub h divided by 1.7 A sub 0 h squared. Now the P sub h and A sub h it will be better if I talk about it in just a minute. Okay, so well, it needs to be exactly defined. So let me wait. So this is basically the those pop-ups are coming. The shear stress, so square root of the sum of the squares of the shear stress and the torsional stress shall not be any more than phi times the shear stress, how should I say, the shear resisted by the concrete plus the 0.66 square root of f sub c prime, that is 8 square root of f sub c prime in our units. Okay. So square root of the sum of the squares of the shear stress and the torsional stress shall not exceed phi times the shear strength provided by the concrete strength in the terms of stress, the shear stress that concrete alone can resist plus 8 square root of f sub c prime. If it is a hollow section rather than a solid section, we take the sum instead of square root of the sum of the squares. The sum of the shear stress and the torsional stress shall be less than or equal to phi times the same expression on the right-hand side. Here, P sub H is perimeter of center line of outermost closed transverse torsional reinforcement. Perimeter of center line of outermost closed transverse torsional reinforcement. A sub 0 H is area enclosed by that perimeter by central line of the outermost closed transverse torsional reinforcement. This is an illustration of this A sub 0 H. Okay, so here it is straightforward central line of closed transverse torsional reinforcement. Here also it is pretty straightforward. This is a solid section, this is a hollow section, does not make any difference. Here also it is pretty clear cut, I hope. So central line of outermost closed transverse reinforcement. Here it's a more complicated situation. There are 3 pieces if you like, but the shaded area, the white area is A sub 0 H, the area within the center line of the, first of all, the P sub H is the perimeter of the central line of outermost closed torsional reinforcement. A sub 0 H is the area enclosed by that perimeter. That would include any holes that there may be in the section. So A sub 0 H. The commentary on the limitation that we just looked at. The size of a cross section is limited for 2 reasons. First, to reduce unsightly cracking, and second, to prevent crushing of the surface concrete due to inclined compressive stresses due to shear and torsion, the diagonal compression that I talked about. Okay, so this is exactly like putting a limit of 8 square root of f sub c prime on the shear that can be put on a section. When there is shear plus torsion, it gets a little more complicated. And in the case of solid sections, we take square root of the sum of the squares. For hollow sections, we simply add the shear stress and the torsional stress together. And the reason we take square root of the sum of the squares in one case and simply add them together in another case is shown here. So when it is a hollow section, the torsional stresses are in the wall of the hollow section. So are the shear stresses in the walls of the hollow section. And we can simply add the two, the torsional and the shear stresses. However, when it is a solid section, The torsional stresses are still in the walls of the thin wall tube, but the shear stresses are now across the entire cross section. So now we cannot simply add the two together. This is why we take the square root of the sum of the squares. Okay, we are still on this limit, analogous to h square root of f sub c prime. If the wall thickness varies around the perimeter of a hollow section, actual hollow section, the wall thickness varies, then the equation, this limitation, shall be evaluated at the location where the left-hand side is a maximum. Okay, I think it is understandable upon reading. If the thickness varies, then you will check this limitation where it is the most critical. The left-hand side is maximum. If the wall thickness is less than the A sub 0 h by P sub h, A sub 0 h and P sub h were very carefully defined, then, so if the wall thickness is less than that, then you shall, so in this expression, A sub 0 h by P sub h shall be replaced by the wall thickness T. That's what we have done. Okay, so you take 1 A sub 0 h, that is A sub 0 h times A sub 0 h. A sub 0 h divided by P sub h is taken equal to wall thickness if it actually is less than the wall thickness. That's all we are saying. This is again a detail. Now the value of F sub y, this is the yield strength of the longitudinal reinforcement, and F sub yt, the yield strength of the transverse reinforcement used for design of torsional reinforcement, shall not exceed 420 MPa. Very important limit, and you absolutely need to keep in mind with all kinds of high strength steel around. In torsional design, we do have this limit. Okay? That is again to avoid unsightly wide cracking. If the yield strength is lower, the stresses are lower, and then the cracking is more controlled. So the value of F sub y and F sub yt used for design of torsional reinforcement shall not exceed 420 MPa. Where T sub u exceeds the threshold torque, we have to do torsional design. And torsional design means we have to provide design torsional strength at least equal to required strength. This is all strength design, no difference. We do exactly the same thing everywhere. Phi for torsion is the same as P for shear. It is equal to 0.75. This is commentary limiting the value of F sub y and F sub yt used in design of torsional reinforcement provides a control on diagonal crack width. I told you that already. Okay. Yeah, this may be worth reading. I don't know. Maybe not. The factor torsional resistance P times T sub n must equal or exceed the torsion T sub u due to the, this is basic strength design. Okay. Now in the calculation of T sub n, all the torque is assumed to be resisted by stirrups and longitudinal steel with T sub c equal to 0. This I said at the very beginning. This is the basis of the torsional design procedure in 318, the thin wall tube analogy. At the same time, the nominal shear strength provided by concrete, this is interesting, the nominal shear strength provided by concrete, V sub C, is assumed to be unchanged by the presence of torsion. This is kind of important. This is assumption. For beams with V sub U greater than about 80% of phi times V sub C, the resulting amount, this it probably doesn't interest you. This is comparing with older code before the thin wall tube analogy was introduced. Now, the torsional strength T sub n, remember we have to have phi times T sub n larger than or equal to T sub u. What is T sub n? Given by this expression, and I will show you a bit of a derivation in a couple of slides. So T sub n is twice A sub 0. A sub 0, remember, is the area within the shear flow path. Gross area enclosed by the shear flow path around the perimeter of the, okay. A sub 0, this is important. A sub 0 shall be determined by analysis. That is an option available to you. But in design, we typically take it equal to 85% of A sub 0H, the area within, remember, the perimeter of the outermost closed torsional reinforcement. That is something we can figure out very easily. And 85% of that is typically taken as A sub 0. 318 allows us to do that. Okay. If you want to analytically determine the A sub 0, then we have given you a reference that will enable you to do that. The equation for T sub n is based on the space truss analogy with compression diagonals at an angle, assuming the concrete carries no tension and the reinforcement yields. That's important. Concrete carries no tension, reinforcement yields. After torsional cracking develops, the torsional resistance is provided mainly by closed stirrups, longitudinal bars, and the compression diagonals. Concrete still carries compression. Okay, so this is the the thin wall tube space truss. We have longitudinal reinforcement, closed transverse reinforcement. This is the torsion acting on the section. That torsion causes shear on the four faces. Okay, V sub 1, V sub 2, V sub 3, V sub 4 on faces 1, 2, 3, and 4. This is the spiral cracking due to torsion, and the angle, the inclination of those cracks is denoted by theta. I don't know that there is anything else shown. Oh, and the dimensions of the cage are X sub 0 and Y sub 0. Those are taken from the center line of the reinforcement. So X sub 0, Y sub 0. Now the derivation of the nominal torsional strength T sub n. So here we have taken part of this face, part of one face, the front face. Okay, the shear acting is V sub 2. This dimension is Y0 as shown here. Okay, between center lines of the legs. These are diagonal cracks at an angle theta. These are closed transverse reinforcement for torsion. Now the cross-sectional area is A sub T, so that the tension is A sub T times F sub YT. If this is Y sub 0, from here to there is Y sub 0, then the horizon, so this is a crack, the height is Y sub 0, then that horizontal distance is Y sub 0 cotangent theta. from trigonometry. Okay, so the horizontal is the vertical multiplied by cotangent of theta. Okay, so the number of how do I call them, the closed ties that are crossed by a crack is y0 cotangent theta divided by the spacing s. So the number of closed ties crossed by a diagonal crack would be y0 cotangent theta divided by the spacing. So now V sub 2 is the shear flow multiplied by the dimension y sub 0 from the center line to the center line of the reinforcement. Okay. The Q, we said at the very beginning, from strength of materials is T divided by twice A sub 0. So V sub 2 is equal to that. Now, so y0 cotangent theta divided by S is, as I mentioned, the number of closed transverse reinforcement crossed by the inclined crack. So that distance y0 cotangent theta divided by S, the number of stirrups multiplied by the force in each of those closed ties, gives us the total vertical force in however many closed ties have been crossed by the crack. This vertical force has to be equal to that shear for vertical equilibrium. Okay? So this is equal to that. This is equal to that. That will make T equal to the right-hand side. If you transpose everything to the right-hand side, you will get that expression. And since the reinforcement is yielding, the transverse reinforcement is yielding, this is the highest torsion that can be carried. So this is T sub n. Okay. So all we are doing is writing the equation of vertical equilibrium. This shear is equal to the total tension in the ties that are crossed by the inclined crack. So the expression for T sub n that we rewrote it, theta shall not be taken smaller than 30 degrees nor larger than 60 degrees. It shall be permitted to take theta equal to 45 degrees for non-pre-stress members or members with less pre-stress than indicated here. Okay. So 45 degrees for non-pre-stress members. 37.5 degrees for pre-stress members with effective pre-stress not less than, I'll let you read that. So the theta is between 30 and 60 degrees. We typically take it as 45 degrees for non-pre-stress members. The additional area of longitudinal reinforcement to resist A sub L, not resist A sub L, to resist torsion. The additional area of longitudinal reinforcement to resist torsion, that is A sub L, shall not be less than given by the right-hand side of this expression. Okay, so we have closed transverse reinforcement A sub T, and we have the additional longitudinal reinforcement, additional to whatever we need for flexure and axial loads. Okay. A sub L shall not be any less than given by the right-hand side, where theta shall be the same value used in equation, the previous equation for T sub n, and A sub T over S shall be taken as the amount computed. So A sub T over S shall be whatever we used here. Same A sub T over S will go into the calculation of A sub L, the minimum longitudinal torsional reinforcement that we need. Okay, so A sub L is given by this expression. Theta shall be the same value that we talked about before, between 30 and 60 degrees, typically taken at 45 degrees for non-pre-stressed members. And A sub T over S shall be the same value used in the computation of T sub N. That's what we are saying. Okay. The derivation of this minimum longitudinal reinforcement A sub L is based on, again, equilibrium. I tried to put the derivation on a slide last night and did not succeed. It's not that simple. So I will write it up and we will post it on the portal. Let us not take time on that. So T sub N was derived. A sub L can also be derived from this diagram, and I will write it up on a page and we will post it on the portal. Okay. When combined shear and torsion act, which is typically the case, the total stirrup area, they're calling it stirrup, but it is closed transverse reinforcement, is the sum of the amounts provided for shear and torsion. To avoid the need to provide excessive amounts of longitudinal reinforcement, ACI states that the A sub TS used in calculating A sub L at any given section should be there's a mistake here. So read it. So section should be I see, should be taken as that. That's what is missing. I didn't save it. So A sub T over S used in the calculation of A sub L at any given section should be taken as the A sub T over S calculated at this. I told you that you will use the same value as in the calculation of T sub N. Reinforcement required for torsion shall be added to that required for shear, moment, and axial force that act in combination with the torsion. The most restrictive requirements for reinforcement spacing and placement shall be met. This is not a trivial statement. This is very important. For shear reinforcement, we have restrictions on spacing, size. For flexural reinforcement, and it will go by the most restrictive requirements. For reinforcement, spacing and placement shall be met. So two important notes. Stirrup area for shear A sub B includes all the legs of a given stirrup. Okay, if you have 3 legs, you get the area of 3 legs. While the stirrup area for torsion A sub T is defined in terms of 1 leg only. Okay, torsion. So shear reinforcement, if you actually have 2 legs, the 2 legs will resist shear. But torsion, it is the 1 leg that is doing the job. Okay, torsional. If you visualize torsional shear, then so stirrup area for shear includes all the legs of a given stirrup, while the stirrup area for torsion is defined in terms of 1 leg only. If a stirrup group had more than 2 legs per shear, only the legs adjacent to the sides of the beam would be included in the summation, since the inner legs would be ineffective for torsion. Okay, so both of those notes are pretty important. It shall be this is a I think I'm tempted to skip this. These are a little bit detailed requirements that I don't know are all that important. I'll let you read them. Okay, now details of torsional reinforcement, extremely important. Torsion reinforcement shall consist of longitudinal bars or tendons and one or more of the following. So longitudinal bars and one or more of the following. Closed stirrups or closed ties perpendicular to the axis of the member. Closed cage of welded wire reinforcement with transverse wires perpendicular to the axis of the member. I don't know how much welded wire you have, so I probably will not try to explain this transverse wire. In non-pre-stressed beams, you can also have spiral reinforcement as your transverse reinforcement. Transverse torsional reinforcement shall be anchored by one of the following. Okay, very important stuff. A 135-degree standard hook or seismic hook, which is defined 135-degree bend plus 6 bar diameter extension, except the 6 bar diameter extension shall not be any less than 3 inches. Okay. So for size, so transverse torsional reinforcement shall be anchored by one of the following: a 135-degree standard hook or seismic hook as defined in SEI 318 around a longitudinal bar. Secondly, so this is one or the other. According to SEI's section such and such, those will allow you a 90-degree hook in regions where the concrete surrounding the anchorage is restrained against falling by a flange or slab or similar member. I'll show you pictures. So this is commentary to the requirement. When a rectangular beam fails in torsion, the corners of the beam tend to fall off due to the inclined compressive stresses in the concrete diagonals of the space truss changing direction at the corner. In tests, closed stirrups anchored by 90-degree hooks fail when this occurred, when the covers pulled off, the corners, the 90-degree hooks opened up. For this reason, 135-degree standard hooks or seismic hooks are preferable for torsional stirrups in all cases. Okay, so there is a very good reason for this insistence on 135-degree hooks. In regions where this spalling is prevented by an adjacent slab or flange, ACI relaxes this and allows 90-degree hooks. So these are very good pictures. So at this corner, you will need the 135-degree hooks on the closed transverse reinforcement. At this corner, 90-degree hooks are good enough because this slab will prevent this kind of spalling of the corner. Okay, this slab confines the transverse reinforcement, so now the 90-degree bends are good enough. Longitudinal torsional reinforcement shall be developed at both ends. This is so shall be developed for F sub y. For hollow sections in torsion, the distance from the center line of the transverse torsional reinforcement to the inside face of the wall of the hollow section shall not be any less than 1/2 of the thickness A sub 0 H over P sub H. There is a commentary to that which is more understandable. The closed stirrups provided for torsion in a hollow section should be located in the outer half of the wall thickness, effective for torsion, where the wall thickness can be taken as A sub 0 H over P sub H. That's what we are trying to do. Closed stirrups provided for torsion in a hollow section should be located in the outer half of the wall thickness, effective for torsion. Okay. Minimum torsional reinforcement. A minimum area of torsional reinforcement shall be provided in all regions where T sub U exceeds the threshold torsion. This is extremely important. Minimum area of torsional reinforcement wherever T sub U exceeds the threshold torsion. The minimum is pretty much the same as the minimum shear reinforcement, same or similar expressions, but here it is so 2 legs of torsional reinforcement and the shear reinforcement area. That's what the minimum applies on. Where torsional reinforcement is required by ACI, the minimum area of transverse closed stirrups is equal to that. So A sub B would be all the legs of shear reinforcement and 2 legs of torsional reinforcement. That's what the minimum applies on. And this has been talked about already a couple of times. So torsion is in the walls of the thin tube, and so you get 1 leg on the left wall, 1 leg on the right wall. A sub B, on the other hand, is whatever you have. So the minimum applies on this. If you can get hold of ACI 318 commentary, it will be beneficial to read that. Where torsional reinforcement is required by ACI, the minimum total area now of the longitudinal torsional reinforcement is given by this expression. Okay, so minimum transverse reinforcement, minimum longitudinal torsional reinforcement, and I keep on reminding you this is additional to whatever we have to have for flexural and axial loads. Okay. The A sub T over S shall not be taken any less than given by that expression. F sub YT refers to closed transverse torsional reinforcement. F sub Y refers to longitudinal reinforcement, as I mentioned already. Spacing of torsional reinforcement. So the spacing of transverse torsional reinforcement shall not exceed the smaller of 1/8 of P sub H, the perimeter, remember, of the outermost closed transverse reinforcement. So shall not exceed the smaller of 1/8 of P sub H or 300 millimeters. The spacing of the stirrup is limited to ensure the development of the ultimate torsional strength of the beam, to prevent excessive loss of torsional stiffness after cracking, which I showed you, and to control crack widths. For a square cross-section, the P sub H over 8 limitation requires stirrups at D over 2, 1/2 of the effective depth. Okay. So it is P sub H over 8 or 300 millimeters, whichever is the smaller of the two. The longitudinal reinforcement required for torsion shall be distributed around the perimeter of the closed stirrups, around the perimeter. So flexural steel would be at top and bottom, but this reinforcement is around the perimeter with a maximum spacing of 300 millimeters. The longitudinal bars or tendons shall be inside the stirrups, very, very specific. There shall be at least 1 longitudinal bar in each corner of the stirrups. Longitudinal bars shall have a diameter of at least 0.42 times the stirrup spacing, but not less than number 10. So the longitudinal bars cannot be any less than number 10 in size. So torsional, so that is, and the final requirement is torsional reinforcement shall be provided for a distance of at least b sub t plus d beyond the point required by analysis. So when you no longer require it according to analysis, you shall extend it by b sub t plus d. D is the effective depth. B sub t is the width of that part of cross section containing the closed stirrups resisting tension. Width of that part of the cross section. Okay. I think that is it. So the summary of all the all the requirements for torsional reinforcement that we discussed is here. So stirrup spacing is maximum is 1/8 of p sub h or 300 millimeters, whichever is the smaller of the two. A longitudinal bar shall be at each corner of the closed transverse reinforcement. The longitudinal bar spacing is no more than 300 millimeters. Longitudinal bar diameter no less than 0.42 times the spacing, nor less than number 10. And extended torsional reinforcement distance is b sub t plus d beyond where it is no longer required. So quite a few details that you have to be aware of. Then in SCI 318, there is an alternative design procedure for, this is for basically precast spandrels that are, that have aspect ratio height over. So these are tall, thin spandrel beams for which we do not have to use the thin-walled tube analogy. We can use any design procedure that is the adequacy of which has been shown by analysis and substantial agreement with results of comprehensive tests. Anyway, to cut a long story short, ACI tells you in the commentary, if you use the Zia Shu approach, which was in SCI 318 before it was replaced by the thin wall tube analogy, for these precast spandrels, your design would be satisfactory. This I chose not to cover. This will take us a good hour at least. This is a pretty detailed, intricate design procedure. So that would be our discussion of torsion. I think this is a good time for a break of 5 minutes. So 29 minutes after the hour, we'll come back and I will do the second topic. Whether it will be an hour or a little more, we will see. Okay, so what is coming up, I think, is very important. So in 5 minutes from now. Okay, the 5 minutes are up, so let us start with the second part. I have a lot of slides here, so I don't exactly know what I'll skip, but one thing I think I will skip is the welded wire reinforcement. I do not know how much of it is in use in Bangladesh. Anyway, if you are interested, the slides are here, and I think they will be understandable anyway, just upon reading. Okay, so the first thing is, what is a standard hook? The term standard hook shall mean one of the following: 180-degree bend plus 4 bar diameter extension, but not less than 65 millimeters at free end of bar. So 180-degree bend, 4 bar diameter extension, but the 4 bar diameter shall not be any less than 65 millimeters. This is a standard hook, or a standard hook can be a 90-degree bend plus 12 bar diameter extension at the free end of the bar. Okay, so 90-degree with 12 bar diameter extension, or a 180-degree with 4 bar diameter extension, but the 4 bar diameter shall not be any less than 65 millimeters. So both are standard hooks according to ACI 318. So those are for longitudinal bars. For stirrups and ties, standard hooks are for number 16 bar and smaller, 90-degree bend plus 6 bar diameter extension at free end of bar. So the standard hook for longitudinal bars is somewhat different from standard hook on stirrups and ties. For stirrups and ties, the standard hook is for number 16 and smaller bars, 90-degree bend plus 6 bar diameter extension. For number 19, 22, and 25 bars, 90-degree bend plus 12 bar diameter extension. Or for number 25 bar and smaller, 135-degree bend plus 6 bar diameter extension at free end of the bar. Okay? I think you have to read closely and see what is being said. Standard hook is a hook on a stirrup or cross tie. The term cross tie, again, I let me not spend time on everything now. When we go to seismic detailing, this cross tie will become more than clear. A hook on a stirrup or cross tie having a bend not less than 135 degrees, except that circular hoops shall have a bend not less than 90 degrees. Hooks shall have a 6 bar diameter but not less than 75. So the main thing I should have pointed out is, so standard hook on longitudinal bars, standard hook on stirrups and ties. Okay, somewhat different. Now we are talking about seismic hook. Okay, which is a seismic hook is a standard hook, but it's a special standard hook. A seismic hook has a 135-degree bend, 6 bar diameter extension, but the 6 bar diameter shall not be any less than 3 inches. As I said a couple of minutes ago, I was talking about something else. Okay, so a seismic hook, very, very important in seismic design, as you will see, is a 135-degree bend with a 6 bar diameter extension, but the 6 bar diameter shall not be any less than 75 millimeters. Okay, so this tells you something kind of important. A closed hoop, as it is called in seismic design of ACI 318, can be something like this, closed by seismic hooks. But this is difficult to fabricate and difficult to place. So ACI allows two-piece hoops. Hoop again is a closed piece of transverse reinforcement. So we are allowed two-piece hoops, a U stirrup with 130 with seismic hook at each end, and this is what is called a cross tie, which will close the top, and the cross tie has one seismic hook and one standard hook. Okay, 90-degree bend plus 6 bar diameter extension. If the 90 degrees is on the right face on this hoop, on the next hoop, the 90 degree has to go to the left face and alternate. So the next one, so every other one, the 90-degree hook will be on the right face. Every other one, the 90-degree hook will be on the left face. Okay. So this is a two-piece hoop, which is how typically things are done. And there are also overlapping hooks as shown in the lower picture. So standard stirrup and tie hooks are limited to, I will let you read the commentary. I think in this part, time is rather limited. Okay, then, so standard hook definition now, minimum bend diameters. So all those hooks require bends, 90 degree, 135 degree, 180 degree. Bend diameter. The bend diameter for a reinforcing bar is defined as the diameter of bend measured on the inside of the bar, and it is specified as so many bar diameters. So this table is basically for longitudinal bars. So number 10 through 25 bar size, 6 bar diameter is the minimum bend diameter. Larger bars, 8 bar diameter is the minimum. The very large, our number 11 and number 14, as we call them here, 57 millimeter diameter. 10 bar diameter is the bend diameter, minimum bend diameter. Inside diameter of bend for stirrups and ties. So that was for longitudinal bars, this table. Okay. Now, inside diameter of bend for stirrups and ties shall not be less than 4 bar diameter for number 16 and smaller bars. No less than 4 bar diameters. For bars larger than number 16, these are stirrups and ties made up of bars that are larger than number 16 in size. Then the diameter of bend has to be the same as for longitudinal bars. Okay, so number 16 onwards, you will switch to this table, and the bend diameter will be 6 bar diameter, 8 bar diameter, etc. Although these large bars are not ever used for ties or stirrups. This is welded wire reinforcement. As I said, I will simply skip. Please read it if you are interested. This is a summary of everything that has been said. You saw this picture already. These are standard hooks on longitudinal bars. The 90 degrees plus 12 bar diameter extension, or 180 with an extension of 4 bar diameter, but not less than 65 millimeters. The standard hooks for stirrups and tie reinforcement, it can be a 90 degree with anyway, the picture is very descriptive, and what I said already together with the picture will tell you about the entirety of ACI requirements. This is important. All reinforcements shall be bent cold. You don't apply heat unless otherwise permitted by the licensed design professional. You absolutely do not do it casually. the heating may make it easy to bend the bar, but you don't do it. All reinforcement shall be bent cold. Reinforcement partially embedded in concrete shall not be field bent. This is very serious restriction. Shall not be field bent, except as shown on the design drawings and permitted by the licensed design professional. Has to be shown on the drawings or permitted, not and. Or if it is not on the drawing, it will have to be permitted by the licensed design professional. Field bending of embedded bars. Without authorization of the licensed design professional, field bending is not permitted to bars partially embedded in concrete. Neil Hawkins and one of his students have came up with a paper that is excellent on this subject. They have recommendations concerning field bending in that paper that you can look up, and I have 3 or 4 slides summarizing their recommendations, which I definitely will not go into in this short presentation. But this is very good stuff. If you absolutely have to do field bending of reinforcement, then this Neil Hawkins recommendations are the best that are available to the best of my knowledge. Surface conditions of reinforcement. At the time concrete is placed, reinforcement shall be free of mud, oil, and other non-metallic coatings that decrease bond. Epoxy coating of steel reinforcement in accordance with certain such shall be permitted. Except for pre-stressing steel, steel reinforcement with rust, mill scale, or a combination of both shall be considered satisfactory. There's absolutely nothing wrong with rust. It gives us bond. Normal rust on conventional reinforcement is totally fine, provided the minimum dimensions, including height of deformations and weight of a hand wire brushed test specimen, comply with applicable ASTM specifications. So rust beyond a point is not acceptable, and there is an ASTM spec that controls that. Placing of reinforcement, the tolerances. Okay, so for flexural members, walls, and compression members, flexural members, walls, and compression members, beams, columns, walls. So the tolerance on effective depth, if effective depth is less than or equal to 200 millimeters, is plus or minus 10 millimeters. If effective depth is more than 200, is plus or minus 13. Tolerance on the specified cover. It used to be minimum cover in SCI 318, but at one point, I don't remember, 31802 or 08, we went to specified cover, like specified compressive strength. The engineer specifies the cover, and what we get is the specified value subject to tolerances. Okay? The tolerances on specified cover minus 10 millimeters for the shallower members, and minus 13 for D exceeding 200 millimeters. Okay, there is no given tolerance on the plus side. So the specified cover can be thinner by 10 or 13 millimeters. It can be thicker, but there is no we don't have a tolerance, specified tolerance. Now there is that table is not the whole provision. This is an integral part of the tolerance that we are talking about. Tolerance for the clear distance to formed soffit. Tolerance for the clear distance to formed soffit shall be minus 6 millimeters. So the clear gap between the formed soffit and reinforcement shall be minus 6 millimeters. In addition, tolerance for cover shall also not exceed minus 1/3 of the concrete cover specified in the design drawing and project specifications. So the minus 10, minus 13 that we had on the table in the table is subject to this further qualification that tolerance for cover shall also not exceed minus 1/3 the concrete cover specified. So the specified value is 20 millimeters. The tolerance is 7 millimeters. Okay, no more than that. Okay, so this is in pictures the same thing. The tolerance on D is plus minus 10, plus minus 13, the tolerance on the cover. And there are other tolerances. Anyway, this is a nice picture that you can look up. Some of the tolerances have not been discussed yet here. So this summarizes pretty much the entire discussion on tolerances in this slide set. And this is a very, very nice, clear picture that again is a summary of the discussion. So tolerances for longitudinal location of bends and ends of reinforcement. Tolerance for longitudinal location of bends and ends of reinforcement shall be plus minus 2 inches, plus minus 50 millimeters, except the tolerance shall be plus minus 13 millimeters at the discontinuous ends of brackets and corbels, and plus minus 25 at the discontinuous ends of other members. Okay, so pretty clear cut. You just have to read it once or twice. The tolerance for concrete cover shall also apply at discontinuous ends of members. So the side cover at the discontinuous end will be the same as the cover that we talked about. Welded wire reinforcement, I will skip this. Yeah, this is not welded wire. Okay, so spacing limits for reinforcement. The minimum clear spacing between parallel bars. Okay, minimum clear spacing between parallel bars, very important. In a beam, you have, let us say, 3 bars. What is the spacing between the first and the second and the second and the third? Minimum clear spacing between parallel bars is the larger of the bar diameter and 1 inch. That's what ACI says. Somewhere else in ACI, but BNBC brings it here, and that's how you should read it. So it's the largest of 3 things: the bar diameter, 1 inch, and 1 1/3 times the maximum nominal size of coarse aggregate. Okay, so this is the gap between bars, the clear gap. 1 bar diameter, 25 millimeters, or 1 1/3 times the maximum nominal size of coarse aggregate, whichever is the largest of the 3. Where parallel reinforcement is placed in 2 or more layers, bars in the upper layer shall be placed directly above bars in the bottom layer with clear distance between layers not less than 25 millimeters. This is extremely important. Okay, this is no good. You have 2 bars in this layer, 3 bars in the lower layer. This placement makes this arrangement of reinforcement makes concrete placement very difficult. Okay, the right configuration is this. Okay, if there are 2 bars, one should be here above the corner bar, another should be here above the other corner bar. Okay, then concrete placement is so much easier. This is vitally important. and the gap between the layers is at least 1 inch. Okay, so this gap is larger of bar diameter 1 inch or 1 1/3 times the maximum stone size. That gap is just 1 inch or more. In spirally reinforced or tied reinforced compression members, clear distance between longitudinal bars shall not be less than 1.5 bar diameter, nor less than 40 millimeters, nor 1.33 times maximum nominal size of course aggregate. So this is in spirally reinforced or tied reinforced compression members. The clear distance between longitudinal bars is larger than we just saw. This is now 1.5 bar diameters, not 1 bar diameter, 40 millimeters rather than 25 millimeters, but that has not changed. 1 1/3 times the maximum nominal bar size. Nominal maximum size of course aggregate shall be not larger than. Nominal maximum size of course aggregate shall not be larger than 1/5 the narrowest dimension between sides of forms, nor 1/3 the depth of slab, nor 3/4 the minimum clear spacing between. Anyway, some of these details I think is probably unnecessary to read. The whole thrust here is that concrete should get in. Okay. So concrete should get in. Keep that in mind. That's what all of this is geared towards. Okay. So clear distance between bars or bar bundles. This is what we discussed. So flexural members, 1 bar diameter larger than or equal to 25 millimeters. The stone size is not in 318 but is in B and BC. Compression members that are tied or spirally reinforced, larger than that, 1.5 times larger, 1.5 bar diameter or 40 millimeters. So this is another representation of, so this is the clear spacing between column bars, 1.5 bar diameter, 40 millimeters, 1 1/3 maximum aggregate size. Clear distance limitation between bars shall apply also to the clear distance between a contact lap splice and adjacent splices of bars. This is important. So the clear spacing, if you have spliced bars, the clear spacing will apply to the outside bars in the splice. I don't know how else to say it. So the clear distance will have to be maintained even at the locations of the splices. That's pretty much what we are saying. In walls and slabs other than concrete joist construction, primary flexural reinforcement shall not be spaced further apart than, so this is in walls and slabs. Okay. Reinforcement shall be spaced, not be spaced further apart than 3 times the wall or slab thickness, nor further apart than 450 millimeters. Yesterday, I think we saw in two-way slabs 2 times the slab thickness and 300 millimeters. Now here, this is much more general. Okay, in walls and slabs in general, the spacing shall not exceed the 3 times the wall or slab thickness, nor 450 millimeters. So if it is a wall, maximum spacing is smaller than 3 times the thickness or 450 millimeters. Bundle bars, groups of parallel reinforcing bars bundled in contact to act as a unit shall be limited to 4 in any one bundle. So these are the bundle bars that are typically used: 2-bar, 3-bar bundles. 3-bar bundle can be like this or like that. Okay. This is when you have a lot of congestion of reinforcement. You then bundle the bars because the spacing will then be counted between the bundles, not between individual bars. Bundle bars shall be enclosed within ties or stirrups. Okay, so just like column bars. Bars larger than number 36 shall not be bundled in beams. Okay, in columns you can do it, in beams you cannot. Individual bars within a bundle terminated within the span of flexural members shall terminate at different points with at least 40 bar diameter stagger. So if it is a 3-bar bundle, the 3 bars will be cut off at different locations with a 40 diameter stagger. This is in beams, not necessarily in columns. Spacing limits for reinforcement. Where spacing limitations or concrete cover requirements are based on bar diameter, a unit of bundle bars shall be treated as a single bar of a diameter derived from the equivalent total area. So you will take the total area of the 3 bars in the bundle, and then you will come up with an equivalent diameter. So pi d squared, pi by 4d squared of shall be the total area of the 3 bars in the bundle. I think this language is clear. So the spacing of 1 bar diameter would mean that equivalent diameter of the bundle. Okay, the equivalent diameters are very conveniently given in this table. 2-bar bundle, 3-bar bundle, 4-bar bundle. So if you have 2-bar bundles of number 19 bars, the equivalent diameter is 26.9, 3-bar bundle 33. Okay, this is an excellent picture. Okay, so these are reinforcing bars in 2 layers. We talked about both spacings. This is 1 bundle bar, 1 single bar. That spacing counts. Okay, so this is like a single bar. This is a single bar, and this is the spacing. We talked about the requirement. Here, a bar bundle, above that a single bar, a bar bundle, above that a single bar. This spacing we talked about, and that spacing we also talked about, larger than or equal to 25 millimeters clear. The cover, concrete protection of reinforcement. Unless a greater concrete cover is required by either exposure, severe exposure requirements, or fire resistance requirements. Unless a greater concrete cover is required by severe exposure requirements or fire resistance requirements, specified cover for reinforcement shall not be less than the following. The code has a table. Okay, and I think it is unnecessary to go into this table. You are all familiar with it, but these covers are given. Again, this is important. Unless a greater cover is required by special exposure conditions, if you are in a coastal area with a lot of salt in the air, that cover has to increase, and it may be that fire resistance requirements are such that the cover has to increase. Headed shear stud reinforcement that we talked about yesterday, I think. For headed shear stud reinforcement, specified concrete cover for the heads or base rails, the heads of the studs or the base rails, shall not be less than that required for reinforcement in the type of member in which the headed shear stud reinforcement is placed. Okay, so slab reinforcement has a clear cover requirement of 20 millimeters, so that would be the requirement for the head of the headed stud in a slab. Okay, so this is a headed stud that is reinforcement at the bottom and the top. This cover would be the specified cover for this cover shall be the specified cover for a slab bar. Okay. From the top of the head to the end of the concrete shall be minimum cover, shall be the specified cover for slab reinforcement plus 1/2 of the diameter of this bar. Okay, so the cover over the head of the stud shall be the specified cover for slab reinforcement, 20 millimeters typically, plus 1/2 the diameter of that bar. This I will let you read the similar picture. The difference is there is only bottom bar in the second picture. Now, corrosive environment, definitely very, very important for many parts of Bangladesh. In corrosive environments or other severe exposure conditions, the amount of concrete protection shall be suitably increased. So we are saying that the values in that table shall be suitably increased. Obviously, it is not very specific. And the pertinent requirements for concrete based on applicable exposure categories, those are in the durability chapter, chapter 4, shall be met or other protection shall be provided. So we are essentially saying you shall increase the covers, you shall meet the durability requirements of chapter 4, or other protection shall be provided. You will not only depend on the cover. Maybe you need physical enclosure or things of that kind. Yeah. So for pre-stressed concrete members exposed to corrosive environments or other severe exposure, all this is saying is, so pre-stressed concrete members now can be class U, class T, or class C. U for uncracked, C for cracked, T for transition. And the classification depends on the tensile stress under surface level loads. Okay, if it is more than I think more than 12 makes it, you have to look up the numbers. Anyway, the tensile stress under surface level loads going beyond 7.5 square root of F sub 6 prime, as I recall, in our units, will make a member a class C, cracked member. If there is no tension, then it is uncracked, and in between it is transition. So the cracked members and transition members have the cover requirements of reinforcement. From a cover point of view, the class C and class T pre-stressed members are treated like non-pre-stressed members. Uncracked pre-stressed members are treated preferentially. That's what it amounts to. Okay. Future extensions: exposed reinforcement, inserts, and plates intended for bonding with future extensions shall be protected from corrosion. Everything has been thought about. Fire protection. In the fire protection requirements are not in ACI 318. So we are discussing concrete and ACI 318. Fire resistance requirements are in the building code. In the US, that would be based on the International Building Code. you have fire resistance requirements in BNBC 2020, and in your case, the general building code is BNBC 2020. Okay. So in the general building code, of which this code, meaning 318, forms a part, requires a thick, if the general building code requires the thickness of cover for fire protection greater than the concrete cover in the table, then you will provide the greater cover, whatever is required for fire resistance. Reinforcement details for columns. Okay, important, extremely important stuff. Okay. Slope of inclined portion of an offset bar with axis of column shall not exceed 1 in 6. I don't know how much of it to read or to go to the picture. I think that may be better. So when we talk about offset bar, the lower column is here, the upper column is there. Okay. If this offset is less than 3 inches, this distance from the face of the lower column to the face of the upper column, less than 3 inches, then you can bend the column bar, the bar in the lower column, into the bar in the upper column. Okay, so that kind of a bend is allowed, provided the offset is no more than 3 inches. If you decide for that kind of a bend, the maximum slope is 1 in 6. And then you have to start ties. So if you bend the bar, there is a horizontal thrust. To resist that, you will need transverse reinforcement. Those have to start no more than 6 inches below where you bent it. Okay, and in the upper column, you will start the transverse reinforcement also 6 inches above the I don't know that line is shown properly, 6 inches above the slab. Okay, this is where you will start. If the offset is more than 3 inches, then you cannot bend the column bars, then you have to have dowels. Okay, so here we are showing a separate dowel, that so this dowel will pick up stress from this bar and then will transfer the stress to that bar, and this will be thrust on you if the offset, as I said, is less than is 3 inches or more. So these details are obviously kind of important. The steel code has reference to composite columns, which I'm going to skip. I'll let you read. Composite columns are uncommon. This one was also that. Yeah. Okay. Connections. At connections of principal framing elements, such as beams and columns. Connections of beams and columns. Enclosure shall be provided for splices of continuing reinforcement and for anchorage of reinforcement terminating at such connections. Okay. So if you have a splice or you have hooked your bar for anchorage because the bar ends at a connection between a beam and a column. Connection of principal framing elements. So you have a splice or you have anchorage. Then the splice or that hook that anchors shall have enclosure. Enclosure shall consist of external concrete or internal. So So enclosure may be provided by other concrete members framing in, that will be external enclosure, or you can provide internal closed tie spirals or stirrups. That will be enclosure of the splice, for instance. So you will have closed tie stirrups or spirals around the splice. The word closed is important. So enclosure to a splice shall be provided by closed transverse reinforcement. Open stirrups will not do. Lateral reinforcement for compression members. This is highly important stuff that we use every day. Okay, so this is column transverse reinforcement. Lateral reinforcement for compression members shall conform to provisions of section such and such. Where shear or torsion reinforcement is required, shall also conform to that. So the transverse reinforcement in a column shall also resist shear and torsion. So the requirements of chapter 11 shall apply. Those requirements we will have to satisfy, and in addition there are requirements here for transverse reinforcement in a column. So lateral reinforcement requirements for composite I will skip. So spirals, these are the requirements. Column spirals. Spiral shall consist of evenly spaced continuous bar or wire of such size and so assembled as to permit handling and space and placing without distortion from designed dimensions. For cast-in-place construction, size of spiral shall not be less than 10 millimeter diameter. Very important. Okay, minimum size. Clear spacing between spirals shall not exceed 75 millimeters nor be less than 25 millimeters. So clear spacing no more than 3 inches, no less than 1 inch. Anchorage of spiral reinforcement shall be provided by 1 1/2 extra turns of spiral bar or wire at each end of a spiral unit. This is how you do it. Okay. Spiral reinforcement shall be spliced if needed by any of the following methods. Lap splices not less than the larger of 300 millimeters and the length indicated in 1 through 5. You have to read. So if you have deformed uncoated bar or wire making up the spiral, lap splice shall not be less than the larger of 300 millimeters and 48 bar diameters. That's what we are saying. So you can lap splice the spiral bar, or you can have full mechanical or welded splice in accordance with section such and such. Lateral spiral shall extend from top of footing, so that it goes into excruciating detail. let me show you a picture. So when beams are framing into all 4 faces of the column, the spiral is discontinued at the lowest reinforcement in the beam, and then it picks up above the slab. Okay, the picture is quite clear. Now, when you don't have beams framing into all 4 sides, you will discontinue your spiral here, but now you will have to provide ties as shown in the picture before the other spiral starts. Because there is no confinement coming from the right side in the picture, you will have to confine the longitudinal reinforcement by providing those bars. Otherwise, they will buckle right there at that location. So those are the things that are said in the details. So we are now talking about column ties. All non-pre-stressed bars shall be enclosed by lateral ties at least. These are very, I don't have feel for these numbers because they have been converted, but these are We all know them by heart. This is, yeah. So number 10 tie size for longitudinal bars, number 32 or smaller, number 13. So in our case, number 4 for longitudinal bars, number 36, 43, and 57. So this is number 11, number 14, and I don't know the 57. Anyway, for the large bars, the minimum tie size, tie diameter is half an inch, 13 millimeters. Vertical spacing of ties shall not exceed the smallest of, very, very important, 16 longitudinal bar diameters, 48 tie bar diameters, least dimension of the compression members. We have had this for ages. Okay. So vertical spacing of ties shall not exceed the smallest of 16 longitudinal bar diameters, 48 tie diameter, and least dimension of the column. Then ties shall be arranged. I will not read it. This is vitally important when we talk about ties in a column. This is what we mean. Okay. So please follow me very, very closely. We normally would have one tie all around. Okay. And that is closed in this picture by 135-degree bends. Then the requirements are every other longitudinal bar shall be supported by, shall be enclosed by the corner of a tie or a cross tie. So this bar, that bar, that bar, that bar, every other bar shall be supported by the corner of a tie or a cross tie. So this would require cross ties here and cross ties there. Okay, a cross tie is a bar with a 135-degree hook at one end and a 90-degree hook at the other end, or better in size. Yeah, let us yeah, this is non-seismic. So 135-degree hook at one end and 90-degree hook at the other end. And those would be alternated. If 135 is on this face, on this cross tie, 135 will have to be on the other face, on the other cross tie. Okay. And then the maximum clear spacing between a supported bar and an unsupported bar is 6 inches, 150 millimeters. So if this gap is more than 6 inches, then you would need another cross tie. And that's what happened in this direction. There are only 3 bars. Every other bar has to be supported. So this cross tie would normally not be needed, except that this gap, the clear distance between the 2 bars, is more than 6 inches. Okay. So when we talk about a column cage or column transverse reinforcement, this is what it looks like. Okay. Every other bar shall be laterally supported by a corner of a tie or a cross tie, and the maximum clear spacing between a supported bar and an unsupported bar is 6 inches or 150 millimeters. Ties shall be located vertically, not more than 1/2 a tie spacing above the top of footing or slab in any story, and shall be spaced as provided herein to not more than 1/2 a tie spacing below the lowest horizontal reinforcement in slab, drop panel, etc. This is totally understandable. So you start at 1/2 a tie spacing and you end 1/2 a tie spacing short of the bottom reinforcement in the beam or the slab. There are a few of these details I probably will skip, and I think I have discussed everything in this picture. So it is a good summary of the things that we just discussed. Note here the same thing as with spirals. Since there is no exterior confinement coming, we will have to provide those ties basically inside the joint. This is something else, where anchor bolts are placed in the top of columns or pedestals. Just pretty often, anchor bolts at the top of pedestals. The bolts shall be enclosed by lateral reinforcement that also surrounds at least 4 vertical bars of the column or pedestal. The lateral reinforcement shall be distributed within 125 millimeters of the top of the column or pedestal, 5 inches at the top, shall consist of at least 2 number 13 or 3 number 10 bars. So number 13 is our number 4, number 10 is our number 3. So 2 number 4 or 3, it's better to say these numbers. So 2 number 13 or 3 number 10 bars. Okay, so those are the anchor bolts here. So you have to have ties, as we said, 3 number 10 or 2 number 13 ties within this 125 millimeter distance that go around the vertical bars. Okay, these are the anchor bolts, these are the vertical column bars. We will confine the anchor bolts by providing those ties around the column reinforcement, and there shall be 3 10 millimeter or 2 13 millimeter ties within the 125 millimeter distance. Here, the difference between this and that is the column cage has another bar in the middle. So the ties will look like this. There would be cross ties around the middle bar, and those ties and cross ties have to be provided within the 125 millimeter distance, 3 number 10 or 2 number 13. Okay, so this is vitally important. I was trying to make the point. This was when we went to Chile after the 2010 earthquake, huge earthquake. This was somewhere between Santiago, the capital, and the Pacific coast. The epicentral area, Concepcion, was the town. This was somewhere in between, a small place. We saw a stadium, and the seats had this kind of a fabric roof, if you like, and in this part of the stadium the roof had come down, and when we tried to look for a reason, the roof was supported by those steel columns, or whatever you want to call them, which were mounted on concrete pedestals. Okay, and here you can see signs of failure. Here it has completely pulled out. So those things have pulled out of the concrete. Here you see so these are the anchor bolts that were in concrete and have pulled clearly out, and that brought the roof down. And we are now talking about confining those anchor bolts. Okay, so you see how necessary that is. Now, lateral reinforcement for flexural members. We are talking about compression members so far. It's approaching 10:30, so I do not know. I have a lot of stuff, so I will keep on going for another 20 minutes at least and see what happens, and then maybe the last topic is structural integrity reinforcement. Maybe that will remain not covered. I don't know. I think I should take some questions. This page has my comments. We can skip it. Lateral reinforcement for flexural members. Okay, so let us start here. Compression reinforcement in beams. This is compression reinforcement. Okay, and let me make absolutely clear as I can make it. So let us say at a beam support section, tension reinforcement at the top, and there is reinforcement. Typically, there is reinforcement at the bottom. If it is seismic construction, we insist on having reinforcement at the bottom, continuous reinforcement, and be that as it may. The bottom reinforcement should be considered as compression reinforcement if it is required to carry compression. If it is just sitting there for other reasons, because of structural integrity reasons, because we have insisted that some of the positive reinforcement in the span be continued into the support, it is there, but it is not needed to carry compression, then these confinement requirements that we are discussing do not apply. Okay, the lateral tying, etc., do not. So when we talk about compression reinforcement, it is reinforcement that is required to carry compression by design calculations. So compression reinforcement in beams shall be enclosed by ties or stirrups, satisfying the size and spacing limitations of 7-10-5, those are the column tie requirements, or by welded wire reinforcement of equivalent area. You also have to satisfy shear requirements, torsion requirements, because this is a beam. Now, such ties or stirrups shall be provided throughout the distance where compression reinforcement is required. Okay, where it is no longer required, you don't need the ties and so forth. Lateral reinforcement for flexural framing members subject to stress reversals or to torsion at supports shall consist of closed ties, closed stirrups, or spirals extending around the flexural reinforcement. So torsion requires closed reinforcement, closed transverse reinforcement, as we have seen. And the same thing is true of stress reversals. If a bar can go into tension and compression because of seismic excitation typically, then we also need closed transverse reinforcement. In seismic construction, we use hoops, not the stirrups. Okay. Closed ties or stirrups shall be formed in one piece by overlapping standard stirrup or tie end hooks around. This is the story. Compression reinforcement is here. This kind of a stirrup would enclose the compression reinforcement. If we want closed transverse reinforcement, this is a way of closing the transverse reinforcement with 135-degree hooks. Okay, and we say alternate because we will typically place the hooks on the left face and then on the next one on the right face, or you can have two-piece hoops like that where there is a class B splice on the two U's are lap spliced with a class B splice. So these are the choices of lateral reinforcement in flexural members. Okay? So in when there is torsion or it is seismic construction, this is the way we go typically. In seismic, this is not allowed, but in for torsion, this can be a solution, although this is not favored because the covers falls off. You are much better off with this kind of transverse reinforcement in beams, as well as obviously in columns. This is required. Experimental tests have shown that where confinement by external concrete is limited, high torsion may result in loss of concrete cover, etc. This we have discussed, and I will skip. I think the bottom line is we have discussed, I think, thoroughly close transverse reinforcement for torsion, and we will thoroughly discuss close transverse reinforcement for high seismic construction. And then if it is not seismic, then something like this would be fine. That is pretty much the bottom line. Okay, you have confined the compression reinforcement, but it is not a closed piece of reinforcement. So with that, I feel comfortable going to the next topic, which is shrinkage and temperature reinforcement. This is substantially important. So reinforcement for shrinkage and temperature stresses normal to flexural reinforcement. This is important. Shall be provided in structural slabs where the flexural reinforcement extends in one direction only. So one-way slab, you shall provide shrinkage reinforcement perpendicular to the flexural reinforcement. Shrinkage and temperature reinforcement shall be provided in accordance with 7.12.2 or 3. Where shrinkage and temperature movements are significantly restrained, the requirements of then it's a different story. Then you have to consider the stresses that can be caused by the restraint. Now it's a substantially different story. So the shrinkage and temperature reinforcement is fine when the shrinkage can, basically when the shrinkage can take place. If the shrinkage is restrained from taking place, then you have to consider the forces that will be caused by that restraint. And I said forces in a general sense. Yeah. So consideration shall be given to effects of forces due to pre-stressing, crane loads, vibration, impact, shrinkage, etc. Estimation of differential anyway. Yeah, this is what I was thinking. The area of shrinkage and temperature reinforcement required has been satisfactory where shrinkage and temperature movements are permitted to occur. Where structural walls or columns provide significant restraint to shrinkage and temperature movement, the restraint of volume changes causes tension in slabs, as well as displacements, shear forces, and flexural moments in columns or walls. In these cases, it may be necessary to increase the amount of slab reinforcement required by 7.12 due to the shrinkage and thermal effects in both principal directions. Topping slabs on precast also experience tension due to restraint of differential shrinkage between the topping and the precast elements or metal deck. There is sometimes topping on metal deck, not sometimes. This is quite popular. That should be considered in reinforcing the slab. Consideration should be given to strain demands on reinforcement crossing joints of precast elements, where most of the restraint is likely to be relieved. Anyway, I can explain everything here, but the main thrust is that the shrinkage reinforcement is good enough when shrinkage is allowed to take place. If shrinkage is restrained, then you have to consider that in providing the reinforcement that you need to provide. Shrinkage reinforcement is 0.18% of gross cross section. For grade 40 reinforcement, it was 0.2%. That reinforcement is now, I don't think is in use anymore. I don't know, this 530 doesn't sound right. So kind of circle it, or yeah, I didn't notice it when I looked at it. So the lower grade, it was 0.2%. That is typically not around. Now it is 0.18% for grade 420. For higher strength reinforcement, we go below 0.18%, but never below 0.14%. That's shrinkage reinforcement. Okay. And this decreasing the amount for high strength reinforcement has been deleted from the code in, I think, 2014 or 2019. So for you, that is there, but here in the US, that is gone. The area of reinforcement given by what you just saw, may be distributed near the top or bottom of the slab, or may be allocated between the two faces of the slab as deemed appropriate for specific. This is something important you need to understand. Shrinkage reinforcement can be placed anywhere you like in the thickness of the member. Yeah, anywhere you like, or you can distribute it between the two faces. This is up to you. Flexural reinforcement has to be near the tension face. Shrinkage reinforcement can be anywhere in the thickness of the member. Now, having said that, I probably overdid it. So nobody in his senses would put the shrinkage reinforcement in the middle of a thick slab. Then it doesn't do you any good. It has to be near the surfaces. Shrinkage starts at the surface. Okay, so you will typically, if it is, you will typically put it at the two faces. Okay, let us. So maybe distributed near the top or bottom of the slab, or maybe allocated between the two faces of the slab as deemed appropriate. You will not put it in the middle. Shrinkage and temperature reinforcement shall be spaced not further apart than 5 times the slab thickness, nor further apart than 450 millimeters. So we have we saw limitations on spacing of longitudinal reinforcement in slabs and things. Those are flexural reinforcement. If it is just shrinkage reinforcement, then the spacing limit is very liberal, 5 times the thickness of 450 millimeters, whichever is the smaller of the two. At all sections where required, reinforce. This is important. This is extremely important. People do not pay attention. At all sections where required, reinforcement to resist shrinkage and temperature stresses shall develop full yield strength in tension in accordance with Chapter 12. And on this reinforcement, when you splice it, you cannot take the AS required over AS provided reduction. Because of that, full yield strength has to be developed. So this is the spacing of shrinkage reinforcement, 5 times the thickness, but no less than 450 millimeters. Okay, footings, I put this in because we used to get, you wouldn't believe how many questions on just this. So this is in, I think this was added in 2008. This section 15.10.4 of SEI 318 your 6810.4 states unequivocally that minimum reinforcing steel in non-pre-stressed mat foundations shall meet requirements of 712 in each principal direction, and that maximum spacing shall not exceed 450 millimeters. So we got infinity of questions. So mat foundations are typically thick. 0.18% of gross is quite a bit of reinforcement. And so there were questions, is it needed, or whatever. So now it is unequivocal. In each direction, you need 0.18% of gross. That is the minimum reinforcement in a mat foundation. 0.18% of gross section in each direction. Okay. Now these are thick members, so you will the placement. The commentary says minimum reinforcing steel may be distributed near the top or bottom of the section, or may be allocated between the two faces of the section as deemed appropriate for specific conditions, such that the total area is 0.18% of gross. So you can put it all on one face or the other face, or half and half at the two faces, 60-40, whatever you like. Now, structural integrity, it's almost a quarter to, so I probably, this is a good topic, important topic. I should spend time on questions, it seems to me. Okay, so let us stop here and let me think if I can pick it up one day. We'll see. Maybe with the seismic discussion, I'll keep it in mind. Okay. So thank you very much, Bodhi. Let us go to questions for the remainder of the hour.
It has already been a bit late.
Yeah, I know.
So I'll just go over a few of them. So I will start with the torsion, the question on torsion first.
Okay.
So for a 4-leg stirrup, say 4 12 mm legs, can we assume the outer leg to transfer the torsion and inner 2 legs to transfer only shear?
No, not only shear. All 4 legs will carry shear. Outer legs torsion and all 4 legs shear.
Yeah. So rest of the questions, I think I answered a few of them, and rest of them Dr. Ghosh already covered in the presentation. So while you were covering, they were asking questions, but I've already covered those. So go over. How should we control the carbonation effect in Bangladesh environment? That is pH 10 to 12.
Read that again.
How should we control carbonation? Just a second, I don't know what is that.
Yeah, somehow the unmuting isn't working today.
Yeah, it's locked actually by WebEx. I don't know how still people are able to unmute.
Okay, so read that again. How do you control the carbonation?
How do you control the carbonation effect in Bangladesh environment, that is having the pH values from 10 to 12 for controlling of rebar corrosion?
Yeah, this is not my subject. I do not, how you control carbonation, I do not know. There are, yeah, keep this question aside. Dr. Rakib is he on today or
No, he's not.
no?
Let
So,
me
yeah,
check
he
once.
he may have an answer, or I might be able to find an answer, but that's not my. I'm not a materials person. I do not know how to control carbonation.
Yeah. For a bar bend more than 3 inches, what is the length of dowel bar? Is it full length of the floor height or half?
You have to read it again.
For bar bends more than 3 inches, what is the length of dowel bar?
It's not making any sense to me. I don't understand.
Maybe more context is needed.
Length of dowel has very little to do with diameter of the bend. So this is why I don't understand. Dowel is something that so think of so we do the footings first, and then the columns go on the footings. Bars stick out of the footing, and those bars are called the dowels, which are then lapped with the column bars. There are no hooks involved in this picture. These are straight dowels that are lapped with the column bars, and that's how construction starts. So 3-inch bend, I honestly don't understand the question. I don't know.
Yeah, I asked him for more context, so let him.
Yeah, yeah.
Is the longitudinal reinforcement of short column, sorry, I will rephrase the question. Can the longitudinal reinforcement of short column be used as anchor reinforcement to resist pull?
Again, I have difficulty answering. Anchor reinforcement is a term that is used in a specific sense. It's a defined term when you go to the in BNBC. It is an appendix. In ACI 318, it was Appendix D on anchoring to concrete. It is now Chapter 17 in ACI 318 in later editions. This anchoring to concrete is, I have to look up, is an appendix in BNBC, appendix to Chapter 6. In there, anchor reinforcement is defined, and anchor reinforcement essentially uh, transfers the stresses from anchors into reinforcement. Anchors are, the headed studs or the headed bolts. Those are the typical anchors. So this anchor reinforcement is kind of continuation of it takes the stress from the anchors into the reinforcement. Now the question is, can the bars in short columns be, read that again?
Yeah, there are so many questions coming. It shifted up.
Yeah.
Oh.
Can be can short
Yeah, can the longitudinal bars be used instead of anchor reinforcement to resist pull? That was the.
Can the bars be used as anchor reinforcement to resist pull?
Yeah, yeah. Longitudinal reinforcement of a short column.
Yeah.
Yeah.
I again would need elaboration before I can answer that question. Yeah, I don't know exactly what he has in mind.
I will ask the same thing. A few of the questions are very general, like. Okay. In footings or pile cap, where should we place the temperature or sinkage reinforcement? In the top of the footing or pile cap?
This I specifically covered the same answer as for mat foundation. It is up to you. If you think it will do the most good near the top surface, that's where you will place it. If you think that the bottom surface, it will do you more good, that's where you will place it, or you can distribute it between the top and the bottom. There is no, that's what it is. You know the situation, and you will, if the top surface is exposed, the bottom surface you think is relatively more protected, you may want to place more of the reinforcement near the top surface and less near the bottom, or all near the top, but it is entirely up to you. The code doesn't restrict it.
That answers almost like 5 to 6 questions. So,
I see.
yeah. So while we are designing a crack section for a slab beam, we need to assign torsional modification factors. What should the factor be? Uh, should it be between 0 and 1?
I don't understand these modification factors. Is it talking about stiffness or what? When you analyze, read that again.
When we design crack section for a slab beam, we need to assign torsional modification factors. So that what factor it needs to apply between 0? Should it be between 0 and 1? Like the question is really framed in a strange way.
No, but I don't understand this modification factor. All I know is EI and GJ. The the flexural stiffness and the shear stiffness, which is also for torsion. So no, I do not understand.
Okay.
Sorry, there are so many questions I don't follow.
The questions are also a bit general, like more context should be provided. What will be the clear spacing of rebars for cast in situ pile according to BNBC?
Cast in place pile, the spacing of reinforcement. I see. I'm hesitating because my first reaction is it is same as column bar spacing, but and I think that is what it is, but I would like to check that. BNBC, I don't know exactly where it is, but in IBC there are detailed pile detailing requirements, and some things are uh, relaxed, like everything that applies to a column doesn't apply to a pile. But the spacing limitations, I believe, are the same. So this will be my answer unless I find something else in that chapter. I would like to check.
Okay.
The spacing between longitudinal bars and so forth is what I was talking about. The spacing of the transverse reinforcement, this is where requirements are relaxed from what they are for the columns of the superstructure. Now, I am now, if you are talking Dhaka, it is design category C or D. Newer parts of Dhaka, it is design category D. So you will have special moment frame columns in your superstructure, and the transverse reinforcement requirements for the piles will be more relaxed. You will not have the very tight tie spacings as in the columns of the superstructure. What they are, without checking, I do not know offhand, but they definitely are relaxed. You don't go with this. You do not have to provide the same confinement to the pile as you do to the column of the superstructure.
Okay. Yeah, a few of the questions Dr. Ghosh has, if you have gone over those topics before, so I don't know, we should address that. But there are lecture recordings already on the portal, so I would recommend you guys to go over those lectures. This has already been answered. If the offset is more than 3 inches, then we should use dowel bars. I wanted to know the embedment length inside the length and free end length above the slab.
Want to know about the embedment length?
Embedded length.
Yeah.
And free end length.
Of the dowels?
Yeah.
Embedded length or what length?
And free end length.
I don't know what that means, but the dowels would have to be lapped with the upper bars and the lower column bars, right? So the lap splice length we talked about within the last, even yesterday there was an example. So you are lapping column bars, and so you will have to provide a class A or a class B splice. Best of circumstances, it can be a compression lap splice. You remember the discussion. So a dowel, if you look at the picture that I showed you, the dowel has to lap with the lower column bar and has to lap with the upper column bar. And the lap lengths have to be sufficient according to, look at the example that we went over yesterday, column bar splices. So that's what you will have to provide. Free end length is not something I understand. There is no free end. The upper part of the dowel is lapped with the upper column bars, and the lower part of the dowel is lapped with the lower column bars.
Right. So the maximum limit of gap between two layers of reinforcement in beam, top or the questions are framed in a very strange way. I would request all you guys to.
No, this question is probably not strange, but so So the minimum gap between the upper layer and the lower layer of reinforcement is 1 inch. Okay. So the question is, if I understand this, is there an upper limit on that gap? The answer is there is no upper limit. But if the further away you go from the tension phase with these layers, the less effective your reinforcement becomes, right? The reinforcement, tension reinforcement is the most effective when it is close to the tension phase. So it will be in your interest to keep the layers as close as possible, not violating that 1 inch gap. So there is no upper limit because who would think of putting an upper limit? It is in your interest to keep the layers as close as possible to the tension phase.
Okay, and I think this will be the last question for today. How many ties should be provided in a beam column joint if the column is not confined by beams at all sides of the column?
How many ties? There is no hard and fast answer like that. The real answer is that if it is seismic design category D, it is special moment frame joint, then I will give you all the details in either next week or the week after. I don't know, is coming up. If it is not a special moment frame, then there are hardly any requirements until ACI 31819. So all you do is provide shear reinforcement, any shear reinforcement that might be needed. So there are really no specific details given for ordinary or intermediate moment frame joints. Special moment frame joints, there are details, very specific details that I will share with you in the next couple of weeks.
Okay, Dr. Ghosh. So rest of the questions, I think more or less you have answered during the presentation and in the question and answer sessions. And
Okay.
might have missed a few questions because there are a lot of questions in between.
Yeah.
Yeah, so the questions are still coming on, so it's difficult.
Yeah,
Yeah.
and I do not know how to deal with them, but we at least have a record of what is coming in, which is good. And we, what I want to say, a couple of things. So this is the end of the concrete lectures that I have planned to do. There is one by Dr. Yazdani tomorrow on pre-stressed concrete. In 8 lectures, I could not cover very important topics like walls and footings. I hope you understand that, and I do not know what the solution is. I tried to fit in as much as I could, and it might have been a little too much, like today. I don't know. Anyway, we did the best we could. Hopefully, it will do some good. And in the case of concrete, because we have a few lectures on seismic design, you will get quite a bit more information that will be more specific to the construction in Dhaka, particularly in the newer parts of Dhaka to the north, where the soils are poor, so that we typically have design category D. So this is one thing I wanted to say. Secondly, the questions I do not know. That we have any solution considering the number that comes in, and also the vagueness or the lack of clarity with which many are written. It becomes difficult to answer them. But whenever there is a little time to regroup, I will see if supplemental material can be provided on the portal. Like I promised an example on slender columns. I haven't forgotten it. Today there was derivation of a torsion formula, the minimum longitudinal reinforcement. Again, I will try to put that in. Anything else that comes to mind within reason, we may try to post on the portal, and then once the pace is such that I think you have, I'm sure that it is impossible to absorb everything. So we will give you time from the end of the instruction to the beginning of the exam, sufficient time that you will have an opportunity to go back to the recordings and make sure that you understand better than you did sitting at the lectures. Okay, with that, thank you very much for showing up every day. And I really am sorry about what you are going through. I know it's a lot of pain, but hopefully professionally it will do you quite a bit of good. And we will continue next week with seismic lectures, which hopefully you will find interesting. Thank you.